start the recording, a picture of each of the model kits that I've got set up. They should all be set pretty darn close to this. I added a few last minute things to them that we'll talk about as we go through the lecture. So if you can build one of these, that would be ideal. Okay? And we will go through and identify the different components of this. Yes, you can steal one. Anybody want one?
Do you require
It is on the list of things as required. I'm not going to... Oh, we're definitely out of model kits.
We can share one.
If we can get some sharing around, that would be ideal. So we may have to get you guys to share. Isaac, did you need one since you're off over there by yourself? Thank you. You don't really need one. If you don't really want one, that's fine. It should help you visualize it. Okay, that's fine. I can leave another one there. Okay, so let's take a look at this kit and see what I've got drawn. So all of the kits that I gave you have actually already formed or done the Diels-Alder reaction. So what we're going to do is split it open. No, I did not put all the hydrogens on there. So what you should be able to do is grab the 2 carbons with either red or brown, or I think it's red and blue, I think is the one other kit, and break those 2 carbons away from the structure. Okay, so that you end up with these 2 pieces. Okay, if you need help with that, I can help you with that too. There is a picture up there that might help you if you're trying to build it. Okay. In that kit, we've got our 2 pieces of our Diels-Alder reaction. We have the diene on the left, and we have the dienophile on the right. Okay. Like I said, we do have an issue because we can't really do those double bonds and still facilitate actually going through the dynamics of this reaction. So acting as our double bond are going to be our quote-unquote p orbitals, which is just the gray hanging bonds coming out of the bottom of that structure. And on our dienophile, it's actually going to be the empty holes coming out the top of that one. Okay? So when we go through to run the Diels-Alder reaction, we will match up these p orbitals, or p orbitals, with the sockets on the dienophile. Okay? So that's the idea, is to go through and run these connections. Once you've got them broken apart, the first thing that I would do is try and align it so that your p orbital bonds are all at the bottom of the structure. Okay? And then what we want to do is go through and effectively do the mechanism where we're connecting our diene to our dienophile in each of these different formats. Okay? So in the first format, our DA1, our Diels-Alder 1, we form one of those bonds first, and we allow for a sigma bond rotation. Prove to yourself that if you do that sigma bond rotation, you do end up with a different product. Okay? So I'm going to give you 5 minutes to play around with this. If you need some help manipulating the structures so you can see it a little bit better, I will definitely come to you to help you out. So Jan, I'll come to you. Oh. So in trying to answer this question, we are going to encounter a couple issues. One, you are playing with models, which is a big issue. Number 2, everything that I've been showing you shows you the sigma down direction of our bond. Is it always going to be sigma down? No, we do also have the option of the sigma up. Is that going to change how those atoms move? No. Okay. Where they're located will still get pushed away from or towards our dienophile. Okay. So if we go through the sigma down process, okay, the first thing that I would attempt to go through and do if I was going to draw an answer, I know this is a Diels-Alder reaction because I have a diene and a dienophile. I got some answers. So here we go. We've got a cyclohexene. I would also go through and add on the substituents that came off of my dienophile. Okay, because I like forming the sigma down, that means those will both be aimed down or away from me. The real question now becomes is what happens to that methyl group? And I'm going to try and minimize rotation, which means I'm going to put the methyl group at that carbon. If I put it on that carbon, what is special about that now black dotted carbon? Chapter 5. It is allylic. It's chiral, which means it is now extremely important where I decide to draw that methyl group. If I draw it up, that's one possible product, or down. The Diels-Alder reaction is going to be based on how those other groups came in. So one answer is correct, one answer is wrong. For those people that were able to play with the model kit, where does that group go? Goes under the structure. Okay. And that's because if we draw in the other atom that's attached, that hydrogen, and this is where I'm going to attempt to play around with this and draw at the same time, our dienophile comes in from the bottom. Where's that hydrogen going to go? Can it fold back down through the dienophile so that it could be aimed downwards? No, it's physically impossible for that to happen. It's going to rotate up away from the dienophile. Well, if the hydrogen rotates up, where does the methyl group go? Necessarily down. Okay? So by using the model kits, we can actually see the easiest way for these things to form and what our natural results are going to be. Yes?
Can you repeat why the hydrogen can't go down?
So let's see. Whose model kit do we want to touch? I don't like your bendy ones. Sorry. So if we take our, see if I can set this up right. So that is on the left, which should be my right. Everybody agree? There's our dienophile, or sorry, our diene. Okay. We take our dienophile, okay, and we bring this in to form that bond. Okay, so from the back side. Can that hydrogen rotate down and through? Let's try it this way. Let's make you do it. If I go through to make that bond, for the hydrogen to be aimed down, what has to happen? You have to rotate that bond. Feel free to rotate it any way you want. You're now butting the hydrogen against the carbon. Oh, well, that's bad. Go the other direction. The only way that you can do it is putting that hydrogen directly up, which means the methyl group must be aimed down. So if you rotate inwards, you run into the dienophile. What if you rotate it outwards? Rotate the structure so that that hydrogen atom is now aimed down. Keep rotating. Oh, but now this atom butts up against the dienophile.
And that has 3 hydrogens already.
And that's going to block it. So we really only have one possible orientation or switch. So if it's aimed inwards on our diene, it's going to aim away from the dienophile. If it's aimed outwards on our diene, it's going to aim the same direction as our dienophile. Okay? So what would we predict for the next product? We started easy. There's our basic structure. If we form the downward side, the methyl group on our top carbon, where should that be aimed? It needs to be aimed upwards, away from. The other one? Down, because it's on the same side. As we rotate in, that methyl is going to rotate downwards because this hydrogen has to rotate upwards to avoid the dienophile. Okay? Really easy to see, right? The model kits help. Okay? I really do honestly believe that the model kits help with that. And if you want help going through and playing with the model kits, we can do that. You'll notice that I've now also specified, I see, give me just a sec, sigma down, see it, for both of those. But realize, these are alkenes. When alkenes react, do we always get the sigma down? No, we also have the sigma up plane. We end up with two possible products. Okay, the relationship between those products are potentially enantiomers, okay, mirror images. So the brief-ish overview is down at the bottom of this page, or the bottom of this slide. What we're looking at is what would the result be for a sigma down bond formation versus if we looked at the sigma up. If you were given a multiple choice exam, okay, they will probably give you one of them. If you're used to looking at the sigma down, they could very well give you the sigma up answer, which is still a possible product. Okay? Equally likely as the sigma down, and you may mistake that for being the wrong answer because it's not the one you're used to seeing. Realize your Diels-Alder will produce two products, minimally, okay, or two possible orientations. You have to then look at those two possible orientations and decide, are they distinct different products or are they identical? Okay? It is extremely tricky. This summary, if you memorize that summary at the bottom, perfect, nailed. You don't have to worry about any of the other stereochemistries or anything else because that gives you all of the answers. Okay? I can't memorize that. Guaranteed. Simone?
Oh, I figured it out.
Oh, good. Questions? Okay, Diels-Alder reactions. Fun stuff. Hopefully that's the end of it. Too bad it's not. Okay, we run into another issue. What if there is no sigma up or sigma down? Okay, is it possible to exclude one of those possible products? Okay, and when we talked about this in lab, yeah, we did come up with an option. We use cyclopentadiene for our diene structure. And why this works is that this sp3 carbon effectively blocks the attack, in this case coming from the top, our sigma up orientation. Okay, so if we went through and formed our sigma up bond, we would expect the product shown. Okay, if we went through and did the sigma down orientation, we'd expect the product shown. Okay, because that sp3 carbon is there, we have effectively prevented the sigma up orientation. How could we prevent the sigma up orientation? This carbon, which I just now made look like an oxygen, this carbon and the big rest of the group of our dienophile run into each other. Well, if they run into each other, they can't get the alkene to wrap around and actually do that reaction. Okay? Everybody kind of comfortable with that? Okay? All we're saying is that those block each other and prevent that kind of sigma up attack. Is there another way I could have drawn this, though? You'll notice in both the sigma up and the sigma down, I've got the maleic anhydride, our oxygens, aimed towards the left. Did I have to have the structure come in from that angle? I could have just as easily flipped this around and drawn the attack like this. Now when it comes in and attacks, I don't get that butting up issue. And if I did the sigma down formation, I still end up with the product that I would have expected from the sigma up orientation. Well, crap. Okay? We thought we'd excluded it, and now it's back to haunt us. It's still there. Okay? What we're looking at in this case is what's known as the endo and exo product formations. Okay? The endo formation takes the withdrawing groups of your diene, your dienophile, and they stack underneath the diene. Okay? That stacking effect, or we won't get into that stacking effect yet. So what we've got is some kind of stacking, vertical axis. If we look at the exo result, we don't see any kind of stacking. We get these two pieces coming in together right next to each other. Okay, so if we took my iPad in my hand, our exo, they come in same plane. The endo, they stack underneath each other and then react. Okay? Two possible products. those of you working on the homework, when we run into two possible products, we can sometimes classify them according to two categories. What are those two categories? Sure. Kinetic and thermodynamic. Okay? I personally find the thermodynamic easier to work with and easier to label. So we'll talk about that one first. If we're going to look at a kinetic versus a thermodynamic product, so if we want something that is thermodynamically favorable, where should the product be? Above or below the reactant as far as energy? It should be lower than it. Okay, so we release that energy off as heat. So that is thermodynamically favored. What if it's kinetic? What is kinetics looking at? How fast the reaction occurs. Does this energy diagram that's just looking at the difference between reactants and products tell us anything about how fast the reaction occurs? No. The only thing we see from the energy diagram, which is officially 152 stuff that nobody ever remembers, this section is thermodynamics. So if I want to look at kinetics, where's the kinetic information found? Our kinetics is found above. Well, what's above our reactant energy? Our transition state. It's the activation barrier. I don't think I like that arrow. Okay, so if we're going to look at our products, let's stick with our thermodynamics. Call this our thermo product. We said we have a kinetic product as a possibility too. Let's assume the kinetic product and the thermodynamic product are different. Okay, so I need another well here, another product that I could show. Where would I place that product as far as energy? Should it be above or below my thermodynamic product? Why should it be above? What happens if it's below? Then that one's thermodynamically favored. Okay, so our kinetic product necessarily must be higher in energy than our thermodynamic product. So let's draw on our kinetic product. Okay. If it's our kinetic product, then something in that upper section that we've got highlighted as kinetics has to suggest that that product would be formed faster. If that product is formed faster, what would I draw in that upper section? Catalyst might be how we would adjust it, but what is that going to show here? We don't want to add extra humps into it. A lower activation energy. With that lower activation energy, it's now kinetically favored. It's going to react faster. Okay? Whereas our thermodynamic product, the product itself is lower in energy, so it's thermodynamically favored. I don't care how fast it happens. When we look at all organic chemistry, it's a balance between kinetics and thermodynamics. Ideally, what do we get when we look at our products? Our product is both kinetically favored and thermodynamically favored. Why would we prefer that situation? We maximize our yield. If we have different possible products for a kinetic and a thermodynamic, that means we get two possible products at the end of it. If we only want one of them, that's a bit of a problem. We automatically start out losing product. Okay? The Diels-Alder is one of these situations where we have a kinetic product that is different from the thermodynamic product. The exo and the endo are those results. Which of these do you think is the kinetic? Which of these is the thermodynamic? That becomes a little bit trickier. Here again, I would evaluate the product to decide thermodynamic stability. Once I've got the thermodynamic one, the other one presumably would be the kinetic. So let's take a look at the products. Which of these would be thermodynamically more stable? So what do we do with a thermodynamic product? We want to stabilize as much as possible. So we want to spread the charge, our electron density, over the largest area possible. Take a look at the endo and exo positions. Yes, it's the same number of atoms, But if we look at the relative area, the exo, we've taken all that electron density and we've now spread it over a plane. Whereas the endo, we ball it all up in one location. You ball it up in one location, what does that do to the overall energy? It skyrockets. Okay? So thermodynamically, our exo product is favored because we've elongated where all that electron density is located. We've made a little bit better. Okay? So our exo is the thermo product, which we could then process of elimination. Let's color code that a little bit better. I'm sorry. Process of elimination means our kinetic is the endo product. Why would the endo product have a lower activation barrier? Comes back to that stacking. If I can stack these things, I can get what's known as a p orbital overlap.
Well, doesn't that increase the
That
because it's it's right there?
everything is stacked nice and tight right next to it. The starting materials are now aligned in just their thermodynamic energy state, where they just sit without having reacted, already in the perfect alignment to form the product. So all we have to do is give it just a little bit of heat, boom, we form the bond. There is no picking up one of those to flip it so that we get the proper orientation for the thermodynamic product. So our endo product is kinetically favored. Our thermodynamic product is the exo product.
Can you explain again why the thermo is the X? Like, I don't see where it's.
So what we're looking at within this structure, so I think the transition states look a little bit cleaner. So if we take a look, I can do it with a couple pens. If we take a look at our pens, our exo product is connecting them like this. We've taken all that electron density and it's now spread across the plane. Our endo product, which we can't really connect in this case, is like this. In the endo situation, we've condensed all that electron density into a space that is relatively compact. Whereas the exo, we've spread that out now over a much larger space. Make sense? Hi. Other question? So our conclusions that come out of this. Our endo is a sterically hindered product. We put a lot of electron density in that same space. So thermodynamically, it's disfavored. But the transition state is significantly lower, which means it is going to be our kinetic product. It's going to form faster. If we go through and look at our exo product, it's sterically spaced. We've gotten that electron density spread out away from each other, which makes it thermodynamically favored, but its transition state is a much higher energy, which means it's a much slower reaction. It's not as quick to happen. Which one happens typically when we run a Diels-Alder reaction? We typically see the kinetic. We almost always see the fastest reaction to occur. What if I wanted the exo product? What would I have to do? I want to add energy, a lot of energy, okay, in the form of heat. If I give the reaction enough energy, I can clear the activation barrier for my exo product, and I can start to form that. But what if it's all already formed the kinetic product? I've got enough heat that the reverse reaction is also possible. So if we give our reaction enough heat and time, even if I do form some kinetic product, it is still in equilibrium with the starting material, and it will go back to the starting material. With that extra energy, I can then form the exo product. But remember, the exo product was thermodynamically favored. The reverse reaction has now such a high activation barrier that we can't clear it. So once we form the exo product, it's now stuck there. It cannot go anywhere else. Okay, so we can push to form the exo product. It just requires lots of time and lots of energy. Okay? I think I saw some hands. Hands? Questions? Yes?
I don't understand what exactly it means when it says it's favored. Like, does that mean
That
that's
phrasing is bad, in all honesty. As soon as I put it up, I was like, that's bad phrasing. The endo product, when you run a Diels-Alder reaction, is the classic result. That is what we expect from a Diels-Alder reaction. So that's kind of where the favored is coming from. When we run a Diels-Alder reaction, almost always we're running under conditions that give us the endo product. Low temperatures and short times. Okay? So if you're asked to provide a Diels-Alder product, they're looking for the endo product. They are not asking for the exo product. Does that kind of help that? That's where the favored is ultimately coming from. So if you're at any question, any Diels-Alder reaction you want, you will have an exo and an endo possibility. The endo is your answer. Every single time, unless they say tons of heat and lots of time. And then you'd have to supply the exo. You're still looking at me quizzically.
Yeah. I guess my question, I might have gotten my labels mixed up, because I labeled endo as a thermal one, right?
No.
Okay, that's why I'm confused.
That's what endo is kinetic. Endo is kinetic.
Okay.
Which actually now, hey, there we go. Push the button and there it shows up. Okay, your endo is your kinetic, your exo is the thermodynamic. It's nice that they give you terms that are so drastically different that you couldn't possibly get them confused while you were talking about it, right? Yes.
If we provide a lot of heat and for a long time,
Yep.
does that mean we only have the thermodynamic product and no endo?
At the limit of a ridiculous amount of time, yes, you would see the favoring of the exo product.
Just one.
Yep. But we look at the opposite limit. We run at cold temperatures, we expect one product as well. It should be mainly the kinetic product, the endo, because there's not enough energy to clear the activation barrier to get to the exo at low temps. Yeah. So you run intermediate temps, that's an awful reaction condition, because now you get both exo and endo all over the place.
And low temp and for long period of time we only have endo.
Low temp and short time.
So if
Right.
long
The longer time shouldn't matter as long as it stays cold. It shouldn't matter as long as it stays cold. Okay? If we want to push a little bit further. Next part of this, what if we want to speed up the reaction? Okay? Like you all thought about when you got in here, how can I get out of here faster? Sorry, there's nothing you can do. Okay? We want to come up with some way to make this reaction go faster. To do that, we want to be able to label our reagents according to the classifications that we've talked about, electrophile and nucleophile. Which of these two reagents is the nucleophile? With an emphasis on the. Really hard to define because the reaction was concerted. If we look at the mechanistic arrows, what happens? Our diene absolutely shares electrons. Cool, it shares electrons, that makes it the nucleophile. But what happens? The other one now, our dienophile, then shares electrons back to the diene, which then very clearly makes it the nucleophile. Well, we just said both of them are nucleophiles. That's a bit questionable. All right? Because of how the reaction works, both of these can act as a nucleophile, both of them can act as an electrophile. Okay? So what we want to do is push this a little bit further. We're now forcing you to say, okay, make a distinction. Which one of these would we predict to act most like a nucleophile? And I personally think it's easier to find the nucleophile. What does a nucleophile have? Electrons. If my nucleophile has more electrons, should it act more like a nucleophile or less like a nucleophile? More like a nucleophile. Which of these two structures has more electrons? The diene. So I would predict the diene to be my nucleophile and my dienophile to be the electrophile. So if I want to speed up the reaction, I've got two choices. Those two choices are make the nucleophile more nucleophilic, okay? Or make the electrophile more electrophilic, right? So if I want to make an electrophile more electrophilic, I want to make those carbons have less electrons around them. What could I attach to that structure to make it have less electrons.
Electron withdrawing group.
An electron withdrawing group, good term. EWG. What would be an example of an electron withdrawing group?
CH.
Chlorine. CH3 is not an electron withdrawing group. Careful.
I was confused here. You're trying to make the dienophile more of a...
More of an electrophile.
Okay.
So we want to make the electrophile more positive. So the things we'll attach to it are going to take electrons away from it. So a chlorine works really well because chlorine is more electronegative than carbon, more willing to take those electrons away. If we do the converse, what happens to the nucleophile? It doesn't really matter where we attach it, at least at this point. What would I want to attach to the nucleophile? An electron. Accepting is withdrawing. Donating. We want an electron donating group. Good donating groups, anything with more electrons than a hydrogen atom, which really covers a lot of bounds. Okay? Carbon, CH3 works, oxygen works. Why do the halogens not work? Halogens have more electrons than hydrogen. If they're electronegative, they don't want to do that donation. Okay? So what we're doing is evaluating what we expect to see out of it, and then we just try and make them more like that situation. Okay, so our diene is most typically classified as our nucleophile, and dienophile our electrophile. There's our electron donating, electron withdrawing groups. All of those are going to be in reference to a hydrogen atom. Why do we use hydrogen atom as our baseline? I'm trying to make it faster than this reaction right here. What are the atoms attached? Hydrogen atoms. That's why I'm comparing to hydrogen atoms. Which brings up another point. What is the charge on a hydrogen atom? Neutral. A hydrogen ion is positive. A hydride ion is negative. A hydrogen atom has one proton and one electron by definition. Okay? So if I want less electrons than a hydrogen atom, the only way I can do that is make sure that whatever that atom is has less electrons than one. What happens if you have less electrons than one? You become positively charged. So our electron withdrawing groups will all carry some form of positive charge on that atom. Our electron donating groups will all supply more electrons than hydrogen, so lone pairs work very well. Or carbons. Carbons don't necessarily have a lone pair, but if they're neutral, they still have more electrons than that hydrogen atom. Okay? We could look at double bonds as well. That's going to bring in another set of ideas that we're going to look at here in a second. Okay? So we've got some examples of electron donating groups and electron withdrawing groups. Everybody relatively happy with donating versus withdrawing groups? Okay, good, because guess where it's going to show up? Chapter 18. Okay? We're going to see electron donating, electron withdrawing groups again. Questions on that, actually, before we step? Okay. Now let's make it really crazy. Okay? We're going to work with these two starting materials. You'll notice that the dienophile I've already got oriented such that it's in the endo conformation. Okay, I've got that carbonyl aimed, that electron withdrawing group aimed towards the left, as opposed to flipped and going the other direction. Okay? You'll also notice that both of them are now asymmetrical. Both the starting material, both the diene and the dienophile. This becomes a bit problematic because now I have two possible orientations for my dienophile reacting. Both of them are endo, but it's now relative to the electron donating group on the diene. Two products can come out of this. Okay? I'm going to give you a minute. Talk amongst yourselves, take a look at it, and try and decide which of those two products is the favored product. Again, We could repeat all that. It's resonance. Okay. Now let's look at our resonance to see how that's going to affect our reaction. I'm going to start with the diene. Take a look at the diene. Where do you think I'm going to start my resonance with? I would argue that there are 3 possible places to start drawing resonance structures with the diene. Where are those 3? Lone pair and both pi bonds. Okay, those are going to be our highest energy electrons. Those are also the only ones we can move in resonance. Of those 3, which one would we look at? Okay, pi bond's not a bad option, and it's not going to take you down the wrong path necessarily, but I would argue that if we simplified and got rid of that electron donating group, that nitrogen, we would have the pi bonds anyway. So we'd end up with the exact same resonance structures with or without that electron donating group. So my argument is that that donating group, that lone pair, is what's characteristically different. I want to start there. Okay? And again, it doesn't matter which one you start with. Okay? So I'm going to start with that lone pair and move the electrons down from the atom to the bond and form a pi bond. How many bonds does this carbon now have? 5. So in moving electrons, that's okay. I'm allowed to put that in that situation, but I now have to fix that problem first. Okay, to fix that, I have to move another pi bond. Well, I've got another pi bond, so I'm going to move it here. What's the issue now? Too many again. So I'm going to move the pi bond again, put it out here. What charge happens now on that bottom carbon? It is now negatively charged. When I go through and run a reaction, I want to put negatives next to positives. I've now found a very negative carbon. So now what do I need to find? A very positive carbon. I get them backwards too. So we can go through and look at how our electron withdrawing group is going to affect this. And again, I would go through that same process. The diene, the alkene of our dienophile, I can draw any resonance I want, but what I want to see is how the electron withdrawing group affects it. Okay? It's going to draw the electron density out of the dienophile, and we could put our negative charge onto this oxygen, right? Well, that's not really part of our dienophile, so that's not super helpful. Is there another charge that got built? Where's the positive? And of course, I picked the wrong orientation. So when I go through and do the Diels-Alder reaction, what do I want to happen? I want this carbon to link to this carbon, and this carbon to link to this one, which means they are now the closest to each other. The top one is our product, which is counter to the steric argument, but the resonance argument in this case beats the steric argument. So Diels-Alder, when you're looking at the regiochemistry, so this is now all regiochemistry, the relative alignment of where those groups are relative to each other in the starting material versus the product. This is our regiochemistry. That is solely dependent on resonance when we look at our Diels-Alder reaction. And yes, we will end up with an enantiomer, I believe. I'd have to draw the other product to look at it to see it. Well, there were a couple hands. Isaac was first. Yeah. Okay, never mind.
Okay, instead of looking at the very beginning, I looked at the end product and saw that there was resonance there, and that's why I picked the top line over that. Would it work
Where's
that
the
way always?
Oh,
resonance?
Because if you look at and you start with the charges with like even just the nitrogen, the oxygen.
Is that a valid move?
Because there's going to be, and then the double bond is going to have the.
Is not attached to that carbon, though. I can't move that lone pair from the nitrogen down. There's nowhere to move it to. Because what you're suggesting then is forming that double bond to the nitrogen, like this. How many bonds does that carbon have? 5. And there's no pi bond to move except the one that you just made.
Oh, okay.
So there's no resonance with the nitrogen. You won't see resonance with the carbonyl either. And this double bond can't rotate up towards it because we still run into that 5 bond issue. Not a bad thought, but unfortunately it didn't work.
Is that long point get implied in your product?
I was afraid someone was going to ask about that as I started to draw them in. We got to be a little bit careful with that because I drew resonance structures and charges.
Right.
Okay. Officially, the charges are on the resonance structure that's not drawn. So if I wanted to do that more appropriately, let me just do it for the this guy. I would show my arrows, and then the result would be this. Now your electrons are balanced. Whereas before, what had happened is I merged those two structures on top of each other, and you're going to run into an electron miscount each time because I've merged two structures that shouldn't be merged.
But the 5 bond ran on nitrogen.
So if we want to go through and do all the way back here and look at its resonance structure. Sorry, it's a little overlap. You can see it?
Yeah.
All right. And that matched the arrows that I drew. Double bond, charge. I'm going to kind of cut you off there, and we can talk about it after class.
Quick question.
Yes?
Why is the top carbon on dienophile more positive than the lower one? How you gotta do it?
When we look at this,
Yeah.
so we just had to reference, it's more positive because this electron withdrawing group is drawing electron density away. This oxygen becomes partially negative,
Okay.
partially positive. We don't want like charges. This one becomes partially negative, partially positive
Okay.
because of that withdrawing effect. Yes? And
Even
then-
with this orientation, we will
Yes.
have only this product.
Yes.
The top structure is the favorite one.
Top one's the favored one. Yeah, I guessed wrong on which orientation to draw the resonance for. The top one is absolutely your favorite answer. Is there another question? Okay, 3?
Yeah. Is the second one be formed or not? Will it
No,
be formed?
no
not-
product
not at
form
all.
for the second one. Nope. Your overall summary for the Diels-Alder, I puts it all together. We start with the diene and the dienophile, go through and make the cyclohexene structure. Your stereo arrangements as your up, down, above. I believe that orientation shown is for the sigma down bond forming. Your diene typically acts as the nucleophile. Your dienophile acts as the electrophile. We do end up with this possibility for enantiomers. Really, the only way to know that is to draw them out and see what the result is. That enantiomer possibility is coming from forming the sigma bond either in the downward direction or the upward direction. Okay. And then your regiochemistry, how the diene and the dienophile line up with each other is dependent on resonance when they go through and form those bonds. Okay. That is now all of everything we're going to talk about in 16 for the most part. There's one question in sapling which I want to address at the very, very end of this, which we will talk about more in lab as well, not with this material. If we take a look at the energy of our diene versus our dienophile, which one is lower in energy? The diene or the dienophile? Why is the diene lower in energy? There's resonance. The double bonds are conjugated with each other. That lowers the energy of that bond. If we're now going to move into spectroscopy, okay, if the energy of that system is lower, what is that going to do to the energy of light that it would absorb? Would we expect the energy to be lower or higher?
Energy of what? Of light?
Of light that it absorbs. It should still be lower. It's lower in energy already. It's still going to continue to go lower. So the energy of light will be lower. Okay, what if we conjugate more double bonds with it? It's going to continue to get lower. Okay, so the energy of light needed to absorb will be lower because as we conjugate more double bonds, the overall energy gets lower. Okay? What's the relationship between energy and wavelength? So everybody has their own way of remembering it. I almost always have to look it up. They're inversely related, so we just stick with that. Lower energy means higher wavelength. Okay? So we get higher wavelengths for more conjugated systems. Okay? As a hint, that is the very last question in Sapling, just so you know, for that chapter. Okay? And we'll talk about that a little bit more when we get into colors and things like that. 17 and 18. I know I only have a couple minutes. I'm not going to go much longer. Nomenclature of benzenes. What is aromatic? So the nomenclature of benzenes, I'm pretty much just going to leave up to you. I'm going to whip through it literally in the next 30 seconds. What is aromatic is a lot harder. There are just some rules that we have to apply to that, and you are expected to know some of those things. So you'll have to memorize those rules. We'll then move into chapter 18, which is looking at all the reactions of benzene. Okay? We'll start with EAS. It's a good thing I've been shuffling order on how I want to talk about these things. EAS is going to be the first thing we'll talk about from chapter 18 for the reactions. We'll then look at the benzylic chemistry, then at Birch reactions, and lastly at the NAS reactions for our benzenes. Okay? So that's the next two chapters kind of outlined. As far as nomenclature goes, those of you that have seen any of my lectures before are probably used to seeing this massive slide that covers everything you could possibly ever want to know about nomenclature, and probably more than you cared to. Okay? All the rules are pretty much up here. With aromatic structures, we get a slight difference in this. Our longest chain with the aromatic structure is typically referred to as benzene. Okay? So we come up with a common name. So if we end up in the lower left-hand corner, this little structure here, we have benzene. If I want to name that compound, well, benzene's my parent name. Do I have any substituents? I have a chlorine. It's now chlorobenzene. Really straightforward. We just kind of attach the names. Okay? An extra piece that shows up that's kind of new for most people. What's this substituent referred to? The NO2? It's a nitro substituent. It's just kind of a common name that comes out of this. You need to know that. So the name for that compound would become nitrobenzene. What happens if we add more substituents? We'd have to go through and number our ring to specify where each of those substituents were. That numbering is going to start at our highest priority substituent. There are a lot of common names that get thrown out there. So this just shows pretty much all the ones you could potentially see. I personally don't expect you to have the common names memorized. I will use them periodically. You may see them also periodically show up on the ACS test. So it is helpful if you review them and at least have a rough idea of what they mean. Okay, as an example, TNT, what does TNT stand for? Trinitrotoluene. So if we're going to put together that name, we'll take toluene, which was the common name given for our very first one, and trinitro means there are 3 nitro groups attached to this. That name on its own is pretty unhelpful because we don't know where those nitro groups are located. All right, so we'd have to add some information. It happens to be at the 2, 4, and 6 positions for your trinitrotoluene. That's about all I'm going to do with nomenclature. Okay? I think, right? Yep, that's all I'm doing with nomenclature. The rest of the material is looking at benzene and what aromaticity